Okay, so in another video, I tried to review a basic first semester of high school physics in preparation for an AP test. Now in this video, I want to review what would be maybe a typical second semester of high school physics in preparation for the AP test. So let's begin. So just hitting the highlights, we have first of all, gravitation. Newton's law of universal gravitation in particular, back from the 1600s, the force of attraction between any two bodies. Again, could be me in this cup, could be me in the Earth, could be you on Mars, could be a satellite and a piece of debris. Of course, when you're dealing with really small things, we don't feel gravity. My head doesn't get pulled into the cup or vice versa. We really experience this with large things, but here it is. The force of gravity, it's going to be the same for both of the objects, right? Is going to be a gravitational constant g, which turns out to be 6.67 times 10 to the negative 11th power Newton meter squared per kilogram squared, times mass 1 and mass 2. It doesn't matter whether you do this one as the Earth or this one as the Earth and this one is me and this one is me, but basically it all comes out the same, divided by the distance between the two bodies in question. So with me and the Earth, it would be the distance, r would be the distance between me and the center of the Earth. Of course, don't confuse capital G, which is this, from little g, which is the acceleration due to gravity near the surface of the Earth, which is 9.8 meters per second squared. They're different. Okay, now gravitational potential energy is very much like the previous equation. The only difference is instead of it being r squared, it's just r. And there's a negative sign in there. This is basically the potential energy, say, of a mass m in relation to the Earth. So the gravitational potential energy at a particular point, what would it be? And so we're kind of focusing on the point above, say, the Earth, rather than on the Earth part. Okay, so we're on to the next topic already, angular velocity. So you remember the big five, you have the velocity equations for linear motion. You can basically substitute in theta for distance and omega for velocity and keep t for time. And if you want, we use a funky version of, instead of a for acceleration, we use a funky a called an alpha, it's Greek. And we have the same thing. So remember that distance equals velocity times time. That's with linear motion. Well, with circular motion, we can say that the angular distance, theta, in radians, equals the angular velocity in radians per second times the time. What is a radian? I'm glad you asked. A radian is basically if you have a unit circle, so a radius of 1. A radian would be the distance around the outside of the circle, basically the circumference of a unit circle. So halfway around a unit circle on the outside is going to be pi radians, and then if you go all the way around a unit circle, the circumference is 2 pi radians. This is based on the circumference. Pi equals the circumference divided by the diameter. And so if you measure the distance around the circumference of a unit circle, it ends up being pi halfway around, 2 pi if you go the whole way around. So theta in angular velocity, an angular distance that is measured in radians, and then omega, it looks like a W, but it's really a Greek omega, is radians per second. So basically, all of the same formulas that you used for linear velocity also work for angular velocity, except we switch out instead of distance in meters, say, we do distance in radians, in basically multiples of and fractions of pi, and then radians per second for omega. T is the same in seconds, and then this alpha is basically acceleration for angular acceleration, which, if you remember, is v squared over r. Remember that from first video? Okay, moving right along. Angular forces. Not going to say a lot here. I don't think the AP exam is going to go too far. So there's something called angular momentum. But as far as I can tell, the AP test doesn't usually go into angular momentum. But center of mass is a concept that you might come across. If you have, so a lot of the physics we look at treats basically big objects as if they're just a point. Well, if you were to take this cup and make it into a point, where would that point be? Well, that's the center of mass. If you were to take all the stuff, you could take me, take a guy, and if you could get me to hold still in one position, then where would be the point where all of that stuff is the mass is centered? Well, here's the equation. The x, where the center of mass is going to be all the different points of the blob times the masses at that point, added up on the top, divided by all the masses. So the total mass is in the bottom, and then the individual masses times the individual positions is the top. And all of that basically ends up being the center of mass. Torque. Torque is something that, again, I'm not sure how deep your AP test would go into it. Torque is angular force. We talk about torque like let's say you're trying to turn a bolt and you have a wrench and it's an old bolt and you can't hardly do it. You're going like this. You're trying so hard to turn that bolt. That's torque. Torque is angular force. And basically the equation is, look, it looks like a T, but it's a funky T. It's a tau. It's a Greek T, tau. So tau, the torque, equals R, which is the lever arm, or not the lever arm, but the distance from, say, the bolt and where you have your hand on the wrench. That's R. And then F is the force that you're exerting, which you're exerting it kind of this way in my example. And then, if you're doing it perpendicular to the wrench, then it's real simple to find the torque. It's just the length of the wrench times the force that you're pulling. But let's say you're doing it at an angle like that. Then the torque is going to be the length of the wrench from the bolt times the sine of the angle that times the force times the sine of the angle that your force is at. So basically, here's a diagram. So let's say I'm trying to pull this lever down, straight down. So the torque is going to be the distance, from the center point, R, times the force that I'm pulling down on, and then times the sine of this theta, which is it's called the lever arm, but that's not important right now. This is a slightly more complicated version. I was looking at a sample problem on one of the AP tests, and it just basically asked what was the torque if you were pulling straight down like this, perpendicular. And in that case, it's just the force times the R. Anyway, may the force be with you. Electric circuits. I'm going out of order. I decided to finish with waves because waves are more complicated. Circuits aren't complicated. Circuits are easy. Current. What is current? Current in a circuit, like in a house, it's the amount of electrons passing a given point in a given time. So if I'm the current keeper, there's an electron, there's an electron. There's going to be lots of electrons. Basically, if 1 Coulomb of electrons are crossing a point per second, that's called 1 amp. So 1 amp is 1 Coulomb passing a point per second. So amp is about the rate of flow of electrons around a circuit, where a circuit is basically, this house, why is the light on? Well, why isn't the light on? The light, when I flipped that switch, what I did is I completed the circuit and allowed the electrons to flow from the power source to that bulb and then back to the power source. So it has to make a complete circuit. When this is off, the circuit is open and no electricity flows. Now it's a closed circuit and electricity flows and the light comes on. I didn't plan that, by the way. It was God. Okay, so voltage, so current is the rate of flow, basically. The rate of flow of electrons in a circuit. Voltage is the push. How much push are the electrons getting? So you probably know that your typical wall socket in the United States is about 110 volts. That it pushes that current, like pushing the swing. Resistance then is the resistance to that push. If there's no resistance, Then the electrons get out of control and they go zzz, you know, and basically everything goes berserk. I did this with my jumping my battery once. I didn't get the red to the red and the black to the black. I switched it up, and I immediately knew I did, because when I completed the circuit, you know, the battery kind of burnt. There's still a burnt mark on that lead on my battery because I shorted the circuit. But anyway, so you want to have some resistance. This light bulb is there's resistance in that light bulb that keeps the electrons from having too good of a time, because you don't want electrons to have too good of a time. It's not right. So here's the equation. Voltage equals current times resistance, or volts, the push, equals the amps, the I, the current, times R, and the unit of resistance is called the ohm, O-H-M. Ohm. So resistance, there's not much resistance to ohm, but an ohm is a unit of resistance. Now power, what is power? Power is the rate at which energy is used up, as it were. And so if you have a very high electric bill, it's because you're using too much power per time. Okay, so but basically power is current times volts. So if you take the current and multiply it by the volts, you're going to get the power, which is in watts. So like a bulb, this, I don't know what this is, a 60-watt bulb means that I'm using up 60 watts a second, I think it is. Anyway, okay, just ignore that. Okay, so series circuits. Resistors add in series. So if you have, and of course the symbol for a resistor, I didn't put it in the video, but it's a jagged kind of up and down is a resistor. If you have one resistor, two resistor, three resistors, four, you know, if they're in a line, then they add up. This resistance plus this resistance plus this resistance plus this resistance equals the total resistance. Now current, that's called series, when everything's just in the same line. Current is the same because the same amount of electrons have to go through the whole thing. They're not diverted off, and so the amperage is going to be the same for every resistor in that series. But voltage isn't that way. Voltage drops per resistor until it gets right back to where it started from. Voltage is kind of like potential energy in a way. You start off, so the electricity comes rushing out, yay, out of the battery, out of the negative side of the battery, and the electrons are like, woohoo, and they go out into the neighborhood, and they go down the hill and down the hill and down the hill and back up. Anyway, but by the time the voltage gets around, it has to all the push is out. They've lost their potential. They've run out of steam by the time the electrons get back to the battery, and they go into the battery, and the battery, you know, is like an elevator that takes them back up, you know, and then they come out again, yay, and then they're full of the push when they come out of the battery. So for each resistance, as it goes around the circuit, you lose some of that potential energy. You lose some of the push in series as the electrons go running through the neighborhood. Parallel circuits are where the electricity doesn't go through the whole thing, but it's diverted into several branches. And the rules are a little different. Now with branches, the voltage is the same across parallel branches, but the amperage will be different, and you have to calculate the amperage in each branch by finding out what the resistance is. So the amperage, you know, if V equals IR, then to find the I in each branch, you divide V by R. So that means you got to find out what the resistance is for each circuit, which, you know, maybe you already know. But the total resistance, what is the total resistance? Let's say you have 4 resistors in branches, and you wanted to find out what the equivalent resistance was for the whole group of resistors. Well, it follows this unfortunately complex pattern. The equivalent resistance is going to be 1 over the sum of all the individual resistances. And that's going to tell you what the equivalent resistance of all the resistance in all those branches is. Amps divide among the branches, as I said. Okay, so Kirchhoff's rules. There may be questions on your AP test about Kirchhoff's rules. So Kirchhoff's first law is the node rule, or the junction rule, that basically says the total current that enters a junction has to equal the amount leaving the junction, so that you have a conservation of charge coming in and going out of each junction. The second law is the loop rule, which basically says what I was trying to explain earlier, that the sum of all the potential differences across any closed loop must be zero, that all the potential has to be used up so that you have a conservation of energy. Okay, Kirchhoff's rules. Not Captain Kirchhoff. Anyway, okay, electric fields. Again, I'm going a little bit out of order, but Coulomb's law is very similar to Newton's gravitational law. If you remember, Newton's gravitational law said that the force of gravity is a constant, capital G, times m1 times m2 all over r squared. Well, Coulomb's law is very similar for the electromagnetic force. For the electromagnetic force, you have a constant K times charge 1 times charge 2 over r squared, where K is 9 times 10 to the 9th power Newton meters squared per Coulomb squared. Now, interestingly enough, electromagnetic force is a little different from gravitational force. Gravitational force is always attractive. The gravitational force always attracts. But the electromagnetic force, like charges repel, unlike charges attract. So sometimes electromagnetic forces repel, woo, like if you have two positives or two negatives, woo. But if they're different, positive and negative, then it's da 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 da, and the positive and negative want to hook up. Okay, now how do we get from the force to the electric field energy at any particular point? So think of a field, you know, kind of a network of lines of force that are going out from a charge, Q. So if you divide the force by a charge, let's say that you're trying to find out what the field is at that particular point. If you divide the force by Q, basically this formula here reduces to this. So this tells you what the energy is at a particular point if you put a test charge there. Okay, so we're getting close to the end. Only two more sections. I'm getting a little bit more complicated the farther we get into this video. So harmonic motion, boing, 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 springs. I actually, in the first video, kind of covered Hooke's law, where X is the amount of stretch beyond the equilibrium point for a spring, and then K is the spring constant, which differs for every spring, and then it's a negative one. So if you want to find out, say, the acceleration, there are some problems that sometimes are on the AP exam with the acceleration of a spring. Basically, you do MA equals this, and then you solve for A. If you know the mass that's being boing, boing, boinged, and the spring constant, and the distance of the amplitude, say, where it's at full capacity, and then you can solve for the acceleration. If it's a vertical spring, boing, then G is the acceleration, and you can solve for the amplitude. What's its maximum displacement of the spring, A, amplitude, for a vertical spring. Potential energy for a spring, I also said this in the previous video, is 1/2 kx squared, which is very much like 1/2 mv squared, isn't it? Anyway, that's neither here nor there. But anyway, kinetic energy is still 1/2 mv squared for a spring as well. So let's say you pull the spring out to its maximum amplitude, then that 1/2 kx squared, when you let go, and it passes its equilibrium point, and it keeps bouncing. But as it passes the equilibrium point, that potential energy will be completely converted into kinetic energy at the equilibrium point, and so 1/2 kx squared here will equal 1/2 mv squared at the equilibrium point. Okay, period and frequency. So a period is the number of cycles. The frequency is cycles. The frequency is the number of cycles per second. There's a name for that, Hertz, because of the fellow that first did the major exploration here. So cycles per second. How many times is it going around per second? That's the frequency. The period is the number of seconds per cycle. It's the opposite of the frequency. And so we say that the period t equals 1 over the frequency, or the frequency f equals 1 over the period. Now, for springs, here is the formula to know, and they'll probably give you this. This is, I think, on the cheat sheet they give you when you're doing the AP exam. But this is the formula to use if you want to find the period of a spring that's bouncing, and where you know the mass that's on the spring and the spring constant. And of course, the frequency is just going to be the flip of that. Okay, for a pendulum, it's a slightly different formula. And again, this should be on your cheat sheet. The period for a pendulum is going to be 2 pi times the square root of the length of the pendulum divided by the gravitational constant, which is 9.8 meters per second squared. Although sometimes they give you problems of pendulums on Mars or pendulums on the moon, and they'll give you what the gravitational constant is for the moon, and you just substitute in that. Waves, the final one. Although this is the most involved. So again, so let's say this is a wave, whatever kind of wave. The wavelength is the distance between crest and crest, or between trough and trough, or from any point to the equivalent point is one wavelength. Okay, and that's a lambda. It's the Greek letter L, stands for wavelength. A is the amplitude. This, of course, would be the negative amplitude. And then the frequency is the number of cycles per second, or it could be cycles per something else as well. Okay, what are the basic rules? Well, velocity equals flip. Velocity flies. I don't know how you want to remember that. But the velocity of the wave, that if you have a traveling wave, is equal to the frequency times the wavelength. This makes sense because the frequency is cycles per second. The wavelength is meters per cycle. Cycles cancel out, you get meters per second, or whatever the unit is. So there are two kinds of waves. There are transverse waves and longitudinal waves. Transverse waves are up and down waves. Longitudinal waves are kind of rarefaction and stretched out accordion waves, as it were. So sound is a longitudinal wave, but a C wave is a transverse wave. Here are a couple of rules. The speed of a wave does not depend. Okay, the speed of a wave v depends on the type of wave, transverse, longitudinal, and the medium, water, string. But the speed of a wave does not depend on the frequency. Okay, the speed of a wave does not depend on the frequency. So you can have a wave that's going like this, but it's still moving at the same rate. So the speed of a wave does not depend on the frequency. It depends on the medium that we're talking about and on the type of wave. Here's rule 2. When a wave passes into a new medium, the speed changes, but the frequency doesn't change. Okay, so a couple things to remember. Transverse waves. These are up and down waves. You have those, for example, on a spring. What is the velocity of a transverse wave? Well, it's going to be the tension force divided by whatever the density of that particular string is. So this has to do with the medium. This is a characteristic of the medium, and this is the tension force involved. And so that's the formula for the velocity of a transverse wave. So m is mu is the name of this. It's a Greek m. Mu is the mass density in mass per space. Volume mass per volume is what that m over L, mass over liters, for example. Okay, so superposition of waves. Constructive interference is where the amplitudes add, and destructive, of course, when the waves are in phase with each other, it adds. But destructive interference is when the amplitudes are not in phase with each other and they subtract from each other. So you can go point by point on the two waves. Let's say two waves run into each other. You can go bit by bit, and where they're the same, it gets bigger, and where they're opposite, they get smaller, and so forth. Okay, beat frequency. If you ever open the window and where only one window is open and you get a kind of very annoying, that's because you have the wave coming in and the wave going out, interfering with each other, and basically the beat frequency of the is going to be frequency 1 minus frequency 2, and it's going to be positive. So that's the absolute value sign. Okay, wave equations. Now, these are a little hard, or at least they look hard, but they're really not as hard as they seem. So let's say that you wanted to find an equation for the change of distance of a spring. So basically, you just plug and play. So if you pull it out to where it's starting from full amplitude, then you're going to do cosine. Why do you do cosine? Because cosine starts with 1, right? Cosine at 0 is 1, and then it goes down. So if you start at full amplitude, you're going to put an A for the amplitude. You're going to use cosine because you started with the maximum. And then 2 pi f times the time. And this is basically an equation for how the x changes with the spring going back and forth. Sometimes, by the way, 2 pi f is written as omega, which is the angular velocity. Omega equals 2 pi f, so that's why we can use those two interchangeably. Now, if you're writing a wave equation that starts from the 0 or from the equilibrium point, then you'll remember that the sign is 0 at 0. And so if you're starting from equilibrium, then you're going to use sine, and then A is the amplitude, 2 pi f, again, f is the frequency, times t. Okay, so these problems are not as hard as they look, because a lot of times it's just a matter of plugging in what they give you to form the equation, or identify the amplitude from an equation they give you, and that sort of thing. Okay, standing waves. Standing waves are, for example, like a violin or a cello. Both ends of the string are fixed with nodes on both ends. And so if you want to know what the wavelength, there are going to be many wavelengths actually, because what happens with these strings is you have what are called harmonics. So you not only have the basic fundamental, which is 2L, basically twice the length. So, and you can see this because if you were to take the middle of the string and pull it up, you would have half of a wave, right? If it went down, it'd be the other half of the wave. But there are these overtones that, for example, if you treat it as having two parts there rather than just one, then it would be one whole wave on the string. And you could do that 3, 4, 5. Actually, I think it's evens for this. But anyway, okay. And then the frequency is just that flipped. So these equations can be used if you have a string that is fixed on both ends. Harmonics, again, are the overtones that by plugging in more than just one. Okay, so standing waves that are open on one end, then it's not twice, but it's 4 times. And again, the frequency is flipped. So basically, when you have the problem, just plug in the number of harmonics or the length of the string and go to town. Okay, longitudinal waves, like sound waves. These are the accordion ones, not the up and down ones, but the accordion waves. Like sound waves, the velocity, again, I assume that if you had a problem like this, they would give you this stuff. So the capital B stands for the bulk modulus, which is a characteristic of the medium, I believe. And then this is, again, a density, a mass per volume. That's the Greek letter rho. It's actually an R. And again, the formulas are similar but flipped. So the 4L formula was for an open-ended string, but here 4L's for closed tube. So this would be like if you're playing a flute. And then for an open tube, it's the 2, where it was flipped the other way. Okay, Doppler effect, last one. The Doppler effect, you know, D stands for the detector, S stands for the source. So if you want to know the frequency of the sound at the detector, it's a function of the frequency of the source, which, as you would expect, so this is where the sound's coming from. And then you have the velocity of whatever it is. Maybe it's a sound wave coming toward you. And so if the pluses and minuses basically have to do with whether the detector and the source are moving toward each other, whether one's moving away. So let's say that the detector is moving toward the source and the source is moving toward the detector. Then both of these would be pluses. Or let's say that the detector and the source are moving away from each other. And then both of these would be minuses. Let's say the detector is moving away, minus, and the source is moving towards, plus. So you adjust the pluses and minuses depending on the way in which the source and the detector are moving in relation to each other. Well, okay, that's a whole lot. In sum, Newton's law of gravitational, we've looked at Newton's law of gravitational universal gravitation. There it is. We've looked at angular velocity. There's just one of the equations. We've looked at torque, which hopefully, if it's perpendicular, it's just R times F. But if they give you a more complicated one, you'll have to do the sine of the angle. Amps, volts, and ohms. V equals IR, P equals IV. In parallel, here's how to find out the equivalent resistance. Coulomb's law, which is very much like Newton's law of universal gravitation. Period and frequency. A period is seconds per cycle. Frequency is cycles per second. There is the way to find out the period of a spring. For pendulums, there's the formula. Again, you'll probably be given these on a cheat sheet. And then lastly, waves. I've ended with, I decided not to repeat a lot of that detail, but just to go with the velocity equals the frequency times the wavelength. And there you have it, a very quick review of second semester physics, high school that is, preparation for the AP exam.